the logistics are same as usual. You can have a cheat sheet, whatever you want on it. Just has to be on the front and back of an 8.5 by 11 sheet of paper. And the structure of the exam will be similar to previous ones, roughly even point split between the three chapters, in this case 25, 28, and 29. And it will be both multiple choice conceptual questions and then calculation based. Roughly, I'd say 60-40 calculation to conceptual. For 25, it's all about capacitance, and it's a whole lot about one very specific thing. So the big ideas are really not that big. It's that a capacitor is something that stores charge, and its ability to do so strictly depends on the size of the plates, how far apart they are, and the dielectric that you've placed in between them. It does not depend on the voltage you put across them, so what kind of battery you connect. It also does not depend on how much charge is on the plates. It just relates those two things. So it says for a certain voltage you put onto the plates, for a certain battery you connect, how much charge will accumulate. Well, you take the voltage of the battery, you multiply by the capacitance, that's how much charge will accumulate. But that capacitance number that you multiplied by, it only depends on the plates themselves and the dielectric in between them. That's really the main stuff for this first part. The question then is just what exact effect does the dielectric have? When you insert a dielectric, it increases capacitance, so it makes it so the capacitor can hold more charge at a particular voltage. How it does that is through polarization. It's an insulator that you've put in between the plates, and when you do so, it polarizes some of the charge in them, and that cancels a little bit of the electric field between the plates and around them, which makes it easier for additional charge to get on. But as far as a conceptual type question about that, it's typically something like, you leave a capacitor connected to a battery and insert a dielectric, what happens? Or you disconnect the capacitor from the battery and insert a dielectric, what happens? Or alternatively, you remove a dielectric, what happens? Or you could change something else about the plates, like the spacing between them, what happens? And I'll get into more details on that once I get through all the chapters, but that's kind of the idea with those types of questions. The rest of the chapter, except I'll come back to RC circuits in a second, is just, I don't know, plug and chug calculations. So from exam 2, we talked about resistors in a lot of detail and did this equivalent resistance thing. You can do the same thing with capacitors. The only difference from resistors is the rules swap. So for series capacitance, you add reciprocals. For parallel capacitance, you add the capacitance itself. That's opposite what we see for resistance. And instead of V equals IR as your thing connecting your two variables, it's Q equals CV. But otherwise, it's the same procedure. You can still identify parallel capacitors, let's say, and they will still have the same voltage across each one. It's just what that implies about the equivalent capacitance is the opposite of what it implied for resistors. For RC circuits, the big idea is just they extend out the time it takes for a capacitor to discharge. If you add a resistor in, it limits how quickly charge can flow onto the plates and how quickly it can flow off. The time it takes is related to this time constant, so RC. And in particular, you'll want to remember, maybe it's a cheat sheet sort of thing, a full charge or a full discharge happens after 5 of those. So it's not just one. After one time constant, you're only down or up 63% of the full charge. Down if it's discharging, up if it's charging up. And that's the main calculation for this part. I won't make you do the logarithm stuff like you had to do on some of the homeworks. It would just be, what is the maximum charge that can accumulate? That's the same as always with capacitors, C times the voltage. What is the charging time? It's 5 time constants. And then for conceptual questions, it's this kind of thing. What happens to different voltages? What happens to the current over time for an RC circuit if it's charging or discharging? I think that's the big stuff for 25. Chapter 28 is the magnetic field stuff. So they point away from north poles and towards south poles. If you put a charge in a magnetic field, it will feel a force, but that force is more complicated than we see for charges and electric fields. What they do in magnetic fields is, for one, they have to be moving, or else they will not feel a force. And that's an easy trick question I can ask is, a charge is placed in a magnetic field. What's the direction of the force on it? And you'll jump straight to right-hand rule, and you'll get it wrong if it's not moving because it doesn't feel a force. Similarly, it has to be moving at least a little bit perpendicular to the field. If it's moving along it in either direction, it will not feel a force. So that's another easy trick question I can ask is, a charge moves upward in a magnetic field that points upward. What's the direction of the force on it? Again, you try and use right-hand rule, but you shouldn't, because there is no force on it in that case. Where you need right-hand rule is for cases where there is at least a little bit of perpendicular motion to the field. And so the right-hand rule is what we've gone over in class. You point your thumb in the direction the charge is moving, you point your fingers in the direction of the magnetic field, and your palm will tell you which direction the force on that charge is. And that's usually what you're looking for with right-hand rule 1. Calculation-wise, it's very straightforward plug-and-chug calculations for the size of the magnetic force. It's just that right there. The only thing that can be a gotcha maybe is you should be able to, from like a diagram, infer that theta is 90 degrees if it is 90. It can be other angles depending on the scenario, but if you've got in your diagram going alongside the question something moving up in a field that points into the page, that automatically means it's 90 degrees. I don't have to tell you that. But that also means you may be hunting for an angle if it's not directly stated. Circular motion in a magnetic field, it's just finding the radius of that circular motion. And then the trickier part is which way will a charge move if it enters a magnetic field. So to answer that, let's say instead of the one we have here, I have some charge just suddenly entering the field and it's moving to the right. Well, my right-hand rule would say my thumb points to the right, the field is into the page, and so the force on that charge would be upward since it's positive, so up this way. That's going to mean that instead of continuing on to the right, this charge will start to deflect upward. If there's more magnetic field up there, it doesn't cut off like it looks like it would in this diagram. So if there's enough for it to keep doing that, it will circulate counterclockwise. So all you need to answer that is your right-hand rule and knowing that that force is going to pull the charge off in the direction the force is acting, and that force acts towards the center of the circle the charge moves on. I ask questions like this a lot, and I see some crazy stuff for the drawings. So if I ask you what path it moves on, and you draw this, even if you said counterclockwise, like we just found out for this charge, your charge I'm asking about isn't on the path you drew. How is it moving in that path if it's not even on it? So, your charge has to be on the path, like in that top circle. That's what I've seen, and I'm always confused. But then it's just getting the direction it circulates correct. All right. I won't do a conservation of energy thing on the exam because that was an exam 2 type question. So I won't test on it again on exam 3. But I could ask about that radius, so the part B question. For Hall effect, I tend to lean conceptual. So it's not calculating a Hall voltage, it's just figuring out which end of a wire becomes positively or negatively charged as a result of the Hall effect. And to answer that, it's still the right-hand rule, but you have to do the direction of electron flow as the velocity or current direction. You can't use conventional current for this, or you will get the wrong answer for which side becomes positive or negative. So in this diagram we're looking at, you got a field that's going sort of into the page, you've got electrons that are flowing to the left, so you use your right-hand rule on that. It's going to predict that a negative charge is deflected upward towards the palm. And that's what we've got going on here. If you did it with positive charge moving to the right, which is conventional current, you would get that positive charge moves to the top of the plate. In other words, the exact wrong answer. So if you see Hall effect or you see which side of a wire becomes positively or negatively charged, you have to use electron flow. You cannot use conventional current for that. You can go back to conventional current if you're just concerned with the force on the wire. So which way is it deflected in a magnetic field? It doesn't matter if it's electrons that hit the wire or positive charges in terms of which way it gets knocked. It's just that voltage that depends on it. So you go back to conventional current for this, you use your right-hand rule, but now your thumb is current flow instead of one charge's velocity. Calculating the force is, again, easy peasy. Just put in the numbers. If I give you 3 out of the 4 main numbers, can you find the fourth, whichever one of them I didn't give you? For torque, again, more conceptual. So which way will a loop of wire rotate in a magnetic field? How do you find that? The easiest way, in my opinion, is not to think of it in terms of this normal vector lining up with the field, although that is correct. The easiest way is just to apply the right-hand rule to both sides of the wire. So for instance, right here, we've got a current coming out of the page, so that would be my thumb out of the page. We've got a field to the right. My palm is going to face towards the top of the page. And so the force is in that direction on that side of the wire. On the other side, thumb is into the page, field is still to the right, so my palm faces downward. And if you've ever taken a right turn in your car, you know that your hands do the same thing to turn the wheel clockwise. That's going to cause a clockwise rotation. One hand on the left pulls up, the other pulls down. And you can also apply it for when the loop is fully aligned, and you'll find that you get no torque because that's not going to rotate the loop. It's just going to stretch it out. If there is a calculation for a motor, again, it's just smashing all the numbers together in the right way. Chapter 29, you don't need Biot-Savart because that's our way of deriving certain magnetic fields. You do need the right-hand rule number 2. And it is another one I'll come back to in a little bit, but it trips people up probably the most between the two right-hand rules. It does say a different thing than the first one. The first one is about finding the force on a charge due to some outside magnetic field. This one is about finding the magnetic field a moving charge creates. It is straightforward as far as the picture goes. You put your thumb in the direction the current flows, you grab onto the wire, your fingers wrap around the same way the field does. What gets messed up is if I ask at a specific point, what is the direction of the field? So, for instance, right here, or right here, where I've got these arrows, and how you figure that out is, at least the easiest way I've found, is imagine a car driving around in the direction that the field circulates. That's the part that's easy to figure out. You just grab onto the wire. But to answer which way the field is pointing at any specific location, so like here, which way would that car be facing if it's driving in a counterclockwise loop? It'll be facing into the page, in this perspective view, at least. And you can apply that to a straight wire. That's what we did here. Finding the field of the wire is very straightforward. You just look for the equation for the field of a straight wire. If you're finding the force between two different wires, you have to use both right-hand rules. The first one is going to tell you which way each one would get pulled in a certain field. The second one tells you what kind of fields they're making. So if I look at wire 1 and I want to know what happens to it, first I got to figure out what kind of field it's sitting in. It's sitting in whatever field is created by wire 2. My second right-hand rule is what I use to figure out what that field looks like. I imagine grabbing onto wire 2, my fingers will wrap around it like the circle is going around here. But then I need to know at the location of wire 1, which way is the field pointing. I imagine a car sort of driving around this loop. Now it's a top-down view of that car, but you can imagine there's your little windshield as the driver is heading towards the location of wire 1, and they will be facing upward in this picture. So that's why I drew B2 that way. Then, now that you have the direction of the field from wire 2, you can find the force on wire 1 using the first right-hand rule. Your thumb would point in the direction of current flow, so into the page. Your fingers point upward, and your palm will face to the right. So wire 1's pulled to the right. And then wire 2, after you do the same long, tedious analysis, you'll find it's pulled to the left. This is the shortcut. Like currents attract, unlike currents repel. Okay, we're getting into the stuff that we are going to cover on Tuesday. The main things are going to be, we're going to derive that on Tuesday, that the magnetic field of a full loop of wire, so not just an arc like we're seeing up top, but a full around loop, is just that expression if you're only concerned with the field dead center of the loop. The direction of the field you still use the second right-hand rule to find, but it's only going to be able to tell you the direction of the field at the center of the loop. And to see that, it's easier to go to this picture down here. So it's still that your thumb is in the direction current is flowing. In this case, it's flowing around the loop that way. You imagine grabbing onto that loop. Your hand is going to dip through it one way or the other. In this picture, it dips through to the left. But say current were flowing the exact opposite direction. And so you'd have to flip your hand over and your thumb points down instead. Well, in order to grab the loop, now your hand's going to dip through it to the right. That's the whole thing. Just use that second right-hand rule to figure out which way the field will point, no matter which way current's flowing. So it's same rule, is just sort of an extension of it for a loop instead of a straight wire. You won't need what we put here because it's a more complicated expression, but we'll have to derive it for homework stuff. Ampere's law won't be on there. Solenoids can be on there, but it's another we just have to derive this, and then all you need to do on an exam is, if it's a solenoid, this is how you find its magnetic field. N is the number of loops in the solenoid. So a solenoid is just, instead of a tightly packed coil, all the loops are more spread out like that. Capital N is how many loops there are. L is the length of that solenoid. Little n is the ratio of those two things. It's telling you how tightly packed the loops are into that length. If it's a huge number, you've packed lots and lots of loops in. 1,000 loops per meter, for instance, would be a value for little n. If it's a small number, the loops are pretty spread out from each other. So you might have one loop per meter or something. You would need to calculate that. To figure out the direction of the magnetic field of a solenoid, it's still right-hand rule 2. You just imagine grabbing any one loop making up the solenoid. So you track which way current's flowing, and in this case it's flowing around and around and around like that. You pick any one of those loops, and then you put your thumb on it in the direction current's flowing. Your fingers will dip through, and that the direction the field points, whichever way your fingers dip through. There are other options besides left and right because the loop could be oriented in different directions like this. So if you've got a loop where current's flowing that way versus this way, you try and apply that second right-hand rule to the top picture, your fingers are going to dip through it this way. If you do it with the bottom one, your fingers are going to dip through the other way. But that's the whole thing. And that is going to finish out the chapters. So I'm going to summarize here, and then I'm just going to do a bunch of practice with right-hand rule 1 and 2. So for chapter 25, the big things I tend to ask about are conceptually, what does capacitance depend on? And what doesn't it depend on? If I insert or remove a dielectric, change the spacing of the plates, or some other thing like that, while either, so I do one of those things, but at the same time, either capacitor remains connected to a battery, or it's disconnected, what happens? So what happens to charge, what happens to capacitance, what happens to voltage? And I'll tell you a couple of these, but I don't want it to be like, here's all possible cases. I still want you to have to think about it a little bit. So a capacitor staying connected is going to mean whatever the battery voltage is, that's the capacitor voltage. So this is voltage being fixed. If the capacitor is disconnected from a battery, then there's nowhere for charge to go, so it's stuck on the plates. So charge is fixed. Inserting a dielectric is going to raise capacitance. Removing it is going to lower capacitance. So for instance, if I have a capacitor that I've disconnected from a battery, and then I insert a dielectric, that's charge being fixed. capacitance increasing, what must happen to voltage? Well, because of this relationship between those three things, if this one can't change, but this one went up, this one must go down. So voltage decreases. That doesn't tell you at all why, but it does give the right answer. The reason why is because if you insert a dielectric, that polarization thing happens, and it would be easier for more charge to flow onto the plates if they were connected to a battery, but they're not here. So instead, it's just that the charge that's already there is stored more efficiently. It takes less energy to hold all of that on the plate. That decreases the voltage across the plates. And then the other big calculation thing is just series and parallel capacitance. So if you're given some kind of more complicated circuit with capacitors, I'm just making this up. Can you find the equivalent capacitance? Can you find the charge on any particular capacitor? Can you find the voltage across any particular capacitor? And like with resistors, this expression only applies to a single capacitor, and it only works if you're talking about the voltage across that capacitor, the charge on that capacitor, and that capacitor's capacitance. You can't just put any voltage you want here. So if this is a 120 volt supply, that doesn't mean this is necessarily 120 volts. It's however much voltage is actually across the capacitor you're being asked about. And if you don't know that, you'll have to find it by simplifying down the circuit and then working your way back up. Then RC circuits. So finding max charge, finding charging time, that 5 time constants thing. And then conceptually, I have no idea what's going on outside, but it sounds kind of scary. Conceptually, what happens to current over time for charging or discharging? What happens to voltage across the resistor over time? What happens to voltage across the capacitor over time? I've asked this one several times on past exams, so what happens to current over time? And the answers always baffle me because the question is what happens to current as the capacitor charges? And the choices are it increases, decreases, remains constant, or I think, I forget, it's usually joke answers for the other ones. So, what has to happen so that the whole thing doesn't explode? Current's got to stop flowing at some point because what happens to that charge? It accumulates on the plates. You got to reach a stopping point or else those plates are going to fill up and up and up with charge. You can't do that forever. So it's got to decrease over time, whether you're charging or discharging the capacitor. It's got to stop at some point. For 28, the biggest thing, honestly, is right-hand rule 1 because it shows up in multiple questions. So just getting that down. And we'll do practice with that in a minute. Calculation-wise, the main things you end up ever using are this for the force on a single charge, and this for the force on a bunch of charges, a current flowing. If I'm asking about a charge moving in a circle, here's how you find the radius of that circle. To find which way it goes around the circle, again, it's right-hand rule 1. To find the direction a whole wire jumps in a magnetic field, right-hand rule 1. And Hall effect, specifically which side of a wire becomes positively or negatively charged. And to answer that, you've got to look at the electron flow, not conventional current. All right, 29. Right-hand rule 2 is the big conceptual thing, and you can use it to find the direction of the field for both a straight wire and a loop of wire, or a coil, which is just a bunch of loops, or a solenoid. The only difference between each of them is how strong the field is. So it's the same rule to find the direction of the field of any of them, but different expressions to find the field strengths. For a straight wire, it's mu naught current over 2 pi times how far you are from the wire, radius. For a loop of wire, it's almost the same thing. I see this get swapped a lot, and it's understandable why. You would think the pi would show up in the loop of wire because it's a circle, but no, it shows up in the straight wire expression. So don't get that mixed up. Again, I said for a coil, you won't need the expression that we're going to end up writing for it because it's more complicated. The only exception maybe is if you're at the dead center of a coil, it's a really simple expression. It's just the field of one loop times the number of loops. So it would be mu naught number of loops, I, over 2r. It's really just think of it as if a coil is 5 loops of wire, it's 5 times the strength of one loop. And then solenoid is this, where n is the number of loops per length of the solenoid. And now I'm going to come over to, well, are there any questions before I come over to the camera? So I'm just going to run through a bunch of different examples just to show how I would answer this. So say we've got a charge that is moving upward, so that would be towards the top of like the exam page, and it's a field that points into the page, so that would be X's on the exam page. Moving upward, the field is into the page, so if you're actually looking at your exam, you'd see the X's on here, upward, into the page is into the exam. The force on that charge would be to the left if it's a positive charge, to the right if it's a negative charge, because that would be toward my palm is to the right. If I have a charge that's moving, let's say, to the left in a field that is pointing upward, so to the left in a field that points upward, a positive charge is going to be away from my palm, which is into the page. A negative charge is going to feel a force towards my palm, which is out of the page. If I have a charge that's moving into the page, so it's an X for its velocity instead of for one of the fields, and the magnetic field it's in is to the right, so charge is moving into the page, so you can see my thumb, I'll tilt it a little bit. The field is to the right, don't mind the graveyard of computers. The force on that charge will be downward, so away from my palm, downward if it's a positive charge, and upward if it is a negative charge. What if I have a charge that's moving to the right in a field that is also to the right?
There'd be no force, right?
Exactly. And that one you can't, if you accidentally start doing the right-hand rule, you can kind of save yourself. So it's a field to, or I'm sorry, it's a charge moving to the right, it's a field to the right. Well, my hand can point like that with my thumb to the right, my fingers to the right, no matter which way it's facing. There's not a clear-cut direction for that force. And it's because there is no force there. It's zero. Or a charge is stationary and it's in a magnetic field that's to the right or into the page or whatever else. If it's stationary, which way do I even point my thumb? I don't know, because it's not going anywhere. So yet again, if you start using the right-hand rule, you can kind of catch yourself for that case. But if a charge is not moving, won't feel a force. And last one is if it's moving opposite the direction of the field. So say field's to the right, charge is moving to the left. Well, good luck getting your thumb that way to even make that work. So yet again, I can't because there's no force on that charge if it's moving opposite the field. Let's do a couple more. So charge is moving, let's say downward, and it's in a field that is into the page. The force on that charge is going to be to the right. Away from my palm is to the right. If it's a positive charge, towards my palm is to the, I can't even pull that off, to the left. And let's see, a charge is moving to the right in a field that points out of the page. So I'm going to have to flex a little bit for this one. To the right, field is out of the page. Trying to make that work. Then a positive charge will feel a force downward. A negative charge will feel a force upwards towards my palm. And sometimes you do have to contort like that. I'm expecting to see a lot of that during the exam. If it doesn't look like you're dancing, you're going to fail. Charge is moving out of the page in a field that is to the left. So charge is moving out of the page in a field that is to the left. It's going to feel a force away from my palm, so downward if it's positive, towards my palm, so upward if it is negative. And if we get into like a circulating charge, so it maybe enters a field that is pointing into the page and it's going upward. So moving up, field is into the page. If it's a positive charge, it's going to feel a force to the left, but that's going to make it deflect to the left. So it's going to start moving in a counterclockwise circle off to the left, and the center of that circle is right beside where that charge first entered the field. So somewhere over here is the center of that circle. It's going to circulate around that center point. If it were a negative charge, still entering upward in a field that's into the page, but it's negative, so it feels a force towards my palm, it's going to deflect the other way. And the center will be somewhere over here, and it circulates around that. So it's an added layer of just saying, well, because of that force that I figured out with the right-hand rule, it's going to make the charge do one thing or the other. If it's a wire, it's the same exact right-hand rule. It's just now it's conventional current. So it's which way is positive charge flowing. And usually I don't even try and trip you up by saying electrons flow this way. You got to remember, do conventional current for that. You will get the right answer whether you deal with electron flow or conventional current for the force. For the voltage, the Hall voltage that builds up as a result of the deflection of those charges, that's the thing you got to use electron flow for. So let's say we have a wire. It's got conventional current running from left to right. So just picture a long straight wire. It can be my pen here. And conventional current is flowing this way. And it's in a magnetic field that points into the page. Well, negative charge is flowing the opposite way of the conventional current, so that the electrons in the wire are actually going to the left. So I should use that, and then the field is into the page. And so towards my palm, the force on a negative charge is going to be upward. So the electrons that are flowing in this wire, they're going to be deflected up towards the top of it, which means the top surface of the wire becomes negatively charged, the bottom surface becomes positively charged. You would get the exact opposite answer if you tried to use the conventional current and this right-hand rule. So you have to use electron flow for the Hall voltage, but only the Hall voltage. Everything else in the chapter, conventional is fine. All right, second right-hand rule. So this is the one about what is the direction of the magnetic field created by a current. Well, you've got really two options. It just ends up depending on how the wire is oriented in space. But let's say you've got current flowing upward in a wire. You grab onto that wire. My fingers wrap around, so I'll come up here. My fingers wrap around. In this case, it would be counterclockwise around. Okay, so that's how my fingers wrap to grab the wire. If I want to figure out exactly what the direction of that field is at any point, either you could do what I'm doing right here and just imagine your finger circulating. And then if I want to know over here, I got to stop and say, where's my finger about to go? It's about to continue outward and stop. Where is it about to go? It's going to go to the right. So the field's to the right up here. And over and stop. Which way is my finger about to go? Into the page. And then I go around and stop. Where's my finger about to go? To the left. So that's one way. The other way is, I said, imagine a car driving around in a circle. Which way is it facing over here? Out towards you. It keeps driving around. Which way is it facing here? To the right. Keep going around. Which way is it facing here? Into the page. And then back behind it is going to be facing to the left. If current's flowing the other way in the wire, I grab on the other way. And so the field circulates the other way. It circulates clockwise now. Same deal to find the direction of the field at any specific point, though. I imagine my finger going around and around and around. Which way is it about to go right here? Out towards you. I keep going around. Which way is it about to go? To the left. And then, get this back into frame. Around, and then here it's about to go into the page. and then keep going around, it's about to go to the right. Or imagine a car driving around in a circle. Which way is it facing back behind the wire? It's facing to the right. Here it's heading out towards you. Here it's heading to the left. Here it's heading into the page. All right, this other variant, which we're going to talk about in full detail on Tuesday, is for a loop of wire. So you just take that straight wire, you bend it into a loop. It's the same right-hand rule, but now it's easiest to answer a question about which way the field points dead center of the loop. So this will not tell you exactly which way it faces near the edges, but I'm never going to ask about that. I'm only going to ask about the direction of the field dead center of the loop because that's where it's going to be strongest. How you do this is, we'll say current's flowing this way around the loop. My thumb still goes in the direction current flows. I grab on. Which way are my fingers dipping through the loop? To the left. Okay, by dipping through, I mean I grab on. My fingers can only go in through the left, or I should say in through the right side, pointing towards the left. Or if current was flowing the other way, I grab the loop the other way, and so my fingers dip through it the other way, to the right. Okay, so current flowing this way, field is to the left. Current flowing this way, field is to the right. The only variant on that is if the loop itself is oriented differently. So now say current is flowing counterclockwise. So my thumb grabs on in the direction of current flow. I grab the loop. Now my fingers are coming out towards me, out of the page. What if current flowed clockwise? Well, now my thumb points the other way. Grab on. My fingers dip into the page. So the main takeaway here is don't worry about the wrapping of your fingers in the same way you did for a straight wire. Just think it can only go through the loop one way or the other. In this case, it can only go into the page or out of the page. Those are your only options for this orientation. Yet another orientation. So now say current's flowing counterclockwise again. I'm trying to get it to where you can see it, but man, it's hard. All right, so counterclockwise like that. I grab on. My fingers have to go up through the loop to do that. So the field points up for this loop. If current is flowing the other way, so clockwise, thumb grabs on the other way, and now my fingers dip through downward, so the field is downward. If you have a coil is just a bunch of loops, and each one of them will have current flowing in the same way around it. So you can still use this for a coil of wire. If you have a solenoid is just like a bunch of loops that are spaced out from each other. But they're still each going to have, because current's sort of flowing in and around, and then in the next loop around, and in the next loop around, pick any one of the loops making up the solenoid and do the exact same thing, and you'll still get the right answer for the field of the entire solenoid. Again, we'll see that on Tuesday. But it's not a hard rule. It's just if you don't actually do it and you just do it in your head, your brain can play a lot of tricks on you. So I do recommend for this part having something, having a roll of tape, something circular. It can be like a scrunchie even, but something to bring to the exam so you can't get away with guessing with your brain, because it's happy to do stuff your hand cannot physically do. Your hand is not. For the straight wire, you've got your pen or pencil, so you don't have to worry about that. But I really would recommend for a loop, bring something circular, and that's totally okay. For the first right-hand rule, again, I'm expecting to see hands up, thinking about things. If I don't, I'm going to be worried about you. So it'll feel stupid, but you'll get the right answer. You'll feel more stupid if you didn't do it and get all the wrong answers. Any other questions? All right, well, if not, I'll sign off and try and escape the back rooms that I'm in right now. And y'all have a good weekend. Email if anything does come up. During the weekend is fine. And I'll see you on Tuesday where we'll finish out chapter 29, start 30 if we can. But that'll be the cutoff for the exam is 29. Have a good weekend.